All those funny acronyms are mostly about astronomical instruments. That might give you the impression that we do not take our science seriously. We guarantee you that we do. But what it conveys, I think, is also something that society is very interested to convey, is that we also have a lot of fun doing this. And if you didn't, then of course you would never graduate. As already mentioned, all travel is a matter of space, time, matter and character. We've been talking about space and time, and we've seen that it is possible to travel through the entire now visible universe in your own lifetime, thanks to the laws of relativity. Matter impinges on this subject in two ways, and we're going to treat them separately. First, we talk about interstellar matter. Interstellar matter is this kind of stuff. It consists of something like 3/4 of hydrogen, a little bit less than 1/4 of helium, and this dark sort of crud over here is very, very, very small smoke particles, dust particles, interstellar dust. When you look at that interstellar dust a little bit more closely, you see that owing to gravity, it sort of contracts, and sort of focus on this little thing over here. In the course of time, that then starts to contract, and when it contracts even faster, it starts to rotate. Something where the wind speed, as it were, in interstellar matter gives you this kind of pattern. When this pattern arises, the central part of such a piece of interstellar matter contracts and it starts to form a star. And around that star is leftover stuff. And that leftover stuff is ultimately going to be us. You and I are made out of that sort of stuff. We're made out of star stuff. Every hydrogen atom in your body we owe to the Big Bang. It was created something like 13.8 billion years ago when the universe started. Every carbon atom, every nitrogen atom, every oxygen atom in your body was made inside stars. And that making of heavier elements inside stars makes stars radiate. When you're out in the sun, when you grow something out, you grow plants and things that you feed on, those feed themselves on radiation, astronomical radiation from these stars. That radiation from the star blows up the central part of that disk revolving around this young star that has just started to form. And the radiation melts the ice on the surface of the dust grains in the center over here. This is called the ice zone, the ice line. And outside here, icy grains keep revolving. And because they're icy, they're sticky. And they stick together and they form planets. Planets are an ordinary, totally normal byproduct of the formation of stars. There's 120 billion stars in our galaxy alone, and most of those have planets around them. When the gas in the disk blows away, you have a little atmosphere over here, and the disk in the center here starts to revolve, and matter starts to cluster and clump together, and then form planets. This is a theoretical computation of what happens when a planet starts to form over here. It sweeps away a clean area over around the star here due to the gravitational interaction between the planet and the stuff around it. And this is an observation of an actual planetary system in the process of forming. Now, I already mentioned that we are made out of star stuff. How are we made out of star stuff? We're made out of star stuff thanks to the laws of quantum mechanics. I mean, we just simply said that we owe our ability to travel wherever we want to go in the universe to the laws of relativity. We owe our lives to the laws of quantum mechanics. Quantum mechanics tells us how particles stick together. In this particular display, in this particular display I've shown over here, the blue ones are carbon atoms, the green ones are what is it called? Well, anyway, this is oxygen. These are oxygen atoms, and these are nitrogen atoms. I'm so sorry. Of course, hydrogen is the white stuff over here. This is caffeine. Those of you who have been drinking beer don't know what it is, but it is a ring molecule that is in coffee. Interstellar matter is this kind of stuff. If you pick up one of the dust grains in this interstellar matter over here, you will find that its surface is not smooth. And the bumpiness of that surface is described by the laws of quantum mechanics. And every now and then, atoms coagulate on the surface of those dust grains, and thereby they form chemical reactions. And Interstellar chemistry was originally thought to be completely impossible. You talk to a sensible chemist, they would say interstellar matter, just 1 atom per cubic centimeter, no way. We are very fortunate to have Professor Erwin van Dissuk in our ranks, and she in her PhD thesis showed that interstellar chemistry is in fact not only possible but extremely important, and currently Professor van Dissuk is one of the key astronomers on this planet Earth. This is what you can form in interstellar space, complicated atoms of this general sort. And the curious thing about it is that the chemical bonds that form here between that star stuff are very, very straightforward and simple. And the reason they are simple is because the laws of quantum mechanics. If you want to know one law in quantum mechanics, which you can memorize and which is totally impossible, well, maybe it's impossible also, but it's totally problematic, is the following. Okay? Almost everything is forbidden, except what is allowed, and that is compulsory. Alright? You might think that we're talking about North Korea, but we are talking about the way in atoms. So when you put things together, they don't form a mixture, they form an actual bond. This, for instance, is phosphorus with 4 oxygen atoms attached to it, called phosphate. This is deoxyribose, and you see how totally simple this is, right? Just, you have your carbon atoms and a few oxygen atoms, and that's it. Here, you have guanine. Again, you see the similarity with caffeine, of course. Okay? When you string those together, you get this happening. You get a phosphate group, the sugar group over here, you have this guanine group over here, and then they stick together by these 3 connections over here. And who does that? That is hydrogen who does that. So the atom that we inherited from the Big Bang actually helps to stitch these molecules here together. You will notice that this is very, very, very small and very, very simple. Well, when you stack 3 of these together, the phosphate and sugar groups will stick together also, and they form these 3 steps over here, 3 links. A little bit more further. When you stack these links together a little bit further, this is the kind of molecule that you get. Now, the curious thing is that this molecule is both simple and complicated. And that is what drives our lives. That is what drives living matter on Earth. Every single atom that you see here was made in the stars, except of course the hydrogen that was made in the Big Bang, as already mentioned. Looking across this spiral over here, you get a very, very small number of atoms, and that means that that configuration is very rigid, very simple, very, very straightforward. On the other hand, in the long direction, it goes on and on and on and on and on. The DNA molecule in a human person like you and I is just over 2 meters long. It's just from there to the floor. That is what makes an enormous number of possibilities to make molecules. On the other hand, across, it is only 25 atomic diameters across. It's very, 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 very narrow. And that is what that defines its simplicity. Now, if we ask ourselves, is this going to be the same outside Earth, elsewhere in the universe? The answer is yes, 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 it is. There is no guarantee that living molecules outside Earth are DNA. Almost certainly they're not. Well, there's some biologists who think they are. But the laws of quantum mechanics that describe these bonds over here, the strictness of the binding, everything is forbidden except what's allowed, and that is compulsory. That holds also between the stars. And the length of this, well, that is of course what makes the variety, that makes what it is certain that there is no 2 identical persons on this planet. The mechanisms we see here are the mechanisms of the stars. And therefore, our current understanding of interstellar chemistry and chemistry on Earth makes it much more credible that there would be life outside Earth than it would be in the times of Christopher Huygens. Let us suppose then that there is such a thing. We come to the 4th and final part of our interstellar travel character. What do we expect? What we expect is this. Why do we expect that? Because we're bastards. Because it is the nasty character, the suspicious, nasty, murderous, colonizing character of humans that we see reflected in our expectations of interstellar life. I'm going to argue and conclude in a moment by saying that probably interstellar life is precisely the opposite, and I'll give you reasons why I think that. I will never talk about aliens. I will talk about exo-neighbors, because neighbors are much more friendly. We had Neighbor Day last Saturday, okay? Alien is associated with a kind of nasty, murderous kind of stuff. By the way, one of those movies you showed. Okay. I won't deny, of course, that it makes good movie material, but it doesn't make good science. When? Do we expect this? Well, we don't, because it's too complicated. We don't expect this because it's too complicated. This is too complicated. Maybe we expect something like this. If you were to ask an exo-neighbor to turn their telescopes on Earth and ask what is the dominant life form, they would conclude that the dominant life form on planet Earth is green snot. The vast majority of biomass on this planet is the kind of crud that you find in the oceans and seashores and stuff like that, and also you and I just simply don't get. However, that is not what people in general are interested in. They're interested in not just unicellular life. They're not interested in green slime or purple slime or whatever their slime is going to be outside between the stars. They want, well, us, I suppose. Well, do we get there? This is from the book I started with, from Jules Verne's book, where the Columbia, you could just see the spacecraft traveling in. By the way, the area we talk about numbers in the quiz, right? Anyone remember what the acceleration was of the bullet that these people traveled in Jules Verne's book? An acceleration of 25,000 G. Right? Can you imagine how flat these people are going to be? This is bad enough, okay? I think you remember Saturn V. This is the first moon. This was Apollo 11. It's 5.5 G, and let me tell you, it's nasty. And I've been in one of those centrifuges, and you don't recommend that on your birthday. What do we expect to find? What are expectations? Our expectations were classified by Nikolai Kardashev. Kardashev classified, that's him, Nikolai Kardashev, he classified exo-civilizations. And he did this in a way that for a physicist was very, very nice. Namely, he took something that you can actually observe. The amount of resources that a civilization uses, and in particular the amount of energy that it uses. So, the Kardashev 4 type civilization is a civilization that has colonized our entire universe and can use the resources of our entire universe. There is no physical reason why they cannot do that. Why? We have seen that our Earth, like Einstein, taught us that you can travel to wherever you want to go in the now visible universe within your own lifetime. Lifetimes are typically geared to the orbital period of planets. That's going to be more or less the same throughout the universe. So if there is another Einstein somewhere between the stars, and why wouldn't there be? They can also find the same solution. Is there evidence of a Kardashev type 4 civilization? No, there is not. We have no, absolutely zero evidence that there is a civilization that has colonized our entire universe. Kardashev type 3, as you can imagine, is a civilization that has colonized an entire galaxy. So not the entire universe just yet. Okay. Well, is there a big difference? You may remember from the graph that I showed you that you can travel from one side of this galaxy to another in something like 14 or 15 of your own years. And traveling to the Hubble field takes you only 40 years. That's not so very different. In other words, a civilization that can colonize a galaxy can also, in principle, colonize the entire universe. Do we have evidence of a Kardashev type 3 civilization? No, we do not. Well, easily, a Kardashev type 2 civilization is one that has colonized a star. All right, the entire solar system. So you might think that this crud that is around this star here is an extraterrestrial civilization that has managed to blow itself up. But it isn't. I mean, it's just the kind of dust that I showed to you in an earlier slide. But still, we can think about it. A civilization that harvests the energy of a star does it in this way. It builds a ring around this. This is the first was proposed by Oliver Stapleton in the book. Currently, people call this a Dyson sphere. That's very dumb. I mean, everybody who knows the equations of motion in solar systems will realize that the sphere would collapse into a star. You have to have something in orbit, all right? But once you do, you can still harvest the vast majority of the energy of a star. Seeing those civilizations is going to be fantastically hard, but not impossible. We can turn our infrared telescopes on other stars and try to find out if the infrared radiation that is left over from such an energy harvesting ring can still be seen. Currently there is no evidence of this. So a Kardashev type 3, it's Kardashev type 2 civilization, we just simply do not yet have, but it is within our reach. It is within the reach of our current observers. Now, Kardashev type 1, that we know. What's that? That's us. We are almost a Kardashev type 1 civilization. If we were to plot the amount of resources that we use against the year, you can do this from just economic guesses and things like that. We are at present approximately a 75% Kardashev type 1 civilization. We use almost all the resources of planet Earth, which is the definition of a Kardashev type 1. We don't do very well. We're just devastating our planet rather than going easy, as it were, on our little island in our universe. But also, to have a civilization like this is thinkable elsewhere, and it gives us certain ideas about how we could spot them. Well, one of the ways we can spot your neighbors, your exo-neighbors, is in the following fashion. Suppose that we are here and our exo-neighbors are over there. This is a piece of our galaxy over here. We are streaming our internet into the universe. I mean, the first radio transmissions were made in the later part of the 19th century. It was about just over 100 years ago. Those signals that Morse started, that's all on its way to the stars, right? Currently, the sphere around our solar system that has knowledge in principle of our radio transmissions contains something of the order of 5,000 stars or thereabouts. So they have all heard about this. Have we heard about them? Well, that depends. If we broadcast here, our broadcasting shell goes into the galaxy. And if they live here, they can catch our signals over here. If they start to transmit, their signals go in our direction, and maybe we will catch them here somehow. However, what's the main problem? The main problem is that if our civilization doesn't live very long, the thickness of this shell is not going to be very much. It's going to be about 100 light years or something thereabouts. So by the time they catch our signals, we have already devastated our planet and we don't exist anymore. That would also work vice versa, because one of the key questions is, why haven't we seen anybody? Because we don't know that there exist exo-neighbors. Well, maybe they treat their planet the way we do. Maybe they treat the planet in such a stupid way that their civilization murders itself in a matter of centuries. And still, when we talk about character, can we say something about the actual character of exo-civilizations that we could contact? And I think we can. And in order to see why, we go back to Einstein. We know from astronomy that the typical distance in galaxies traveling with the speed of light is of the order of 60,000 or 100,000 years or something thereabouts. We also know from the computations that I've shown to you in the first part of my talk that same piece of space we can cover in 14 years with a relativistic spacecraft. So yes, we can do it. Okay. But what does this mean about civilization? A Kardashev type 3 civilization that has colonized an entire galaxy must be a civilization with a characteristic time scale of 100,000 years, 50,000, 60,000, 100,000 years. This civilization must be stable on a time scale of 100,000 years. Do we know this? Can we do that? I don't think so. what we can expect. Suppose that we were to encounter a person, an exo-neighbor, from a civilization that has colonized our galaxy. Will they be that sort of aliens with all these teeth and things like that? Will they come and murder our Earth? I think not. Because relativity tells us that a civilization of that type must be stable on a timescale of 100,000 years. We know from experience on Earth that civilizations that are warlike, civilizations that are wasteful, civilizations, in other words, that are stupid bastards, they don't live very long. How long was it that the total reign of Genghis Khan lasted? How long did it take for Alexander, they call him Alexander the Great, how long did it take before that just died out? The worst live the shortest amount of time, 50 years, 100 years. For the victims of such societies, life is very miserable, but astronomically speaking, 50 or 100 years is absolutely nothing. In other words, any civilization of the Kardashev type 3 that we might encounter is, due to the laws of relativity, almost certainly going to be a peaceful society. So when you see something like this, you might think that, these are worlds in collision, was actually the title of one of these SF things in the 1950s. Worlds in collision. Is this a war of the worlds? Well, I don't think so. These are colliding galaxies. We know that war is good for absolutely nothing. And any Kardashev, any advanced Kardashev civilization in our universe will be essentially peaceful. So here's a toast to our exo-neighbors. Thank you very much. I think it's question time. I've learned my lesson now. So